Okay, so this is, we're still on O2C flight instruments. If you don't count the day we watched the videos, this is the third day of lecture, is that correct? Okay, so if you wanted to call it part 3, you could do that. And if I recall correctly, we did this slide before, so please take a look at your notes. I've modified this, and I can't remember if I modified it before or after yesterday's lecture. Is this what you wrote down? No. Okay. So you had indicated, calibrated. Did you have equivalent? Okay, cross out equivalent. Did you have ground speed? Ground? Okay. So I want it to look like this. My apologies. So last time, I showed you a picture of an airspeed indicator, and we started talking about an airspeed indicator a little bit. So you have some clue what an airspeed indicator looks like. It's kind of like a speedometer. It tells you how fast you're going. Speedometers, though, if it's accurate, it tells you ground speed. So I'm going to actually talk about ground speed here first. I actually drive a 2007 Prius, and it actually has a system where it measures how often the wheels spin around. It's got a sensor on the transmission that tells me how often the wheels spin around. But my tires got low, got worn out, and I calibrated my speedometer with the GPS, and it was right on, right exactly accurate. And I thought, okay, interesting. So then I put new tires on it, and I thought, okay, if I put the tires on it, the tires will be a little bit diameter, the wheel can spin a little slower, so my speedometer won't be quite as accurate. But sure enough, I calibrate it and look at the GPS, and it's perfectly accurate. It's because the Prius has a GPS built into it, and unless you go into a tunnel, it gives you the GPS ground speed. So I thought that was really weird. Now, ground speed, if you look at the main that we've talked about, the 6 flight instruments, there's nothing that tells you ground speed. The only way you're going to be able to get ground speed is kind of a navigation computer like a GPS. Basically, GPS are very common in airplanes. And the GPS tells you how fast you're moving across the ground. So let's just say for fun, I'm flying at 100 knots, but I'm flying into a 20-knot wind. My airspeed indicator is, let's just say I'm at sea level, it indicates 100 knots. Because I'm flying into a 20-knot wind. If I turn around and go with the wind, my airspeed indicator may still say 100 knots, but now my ground speed says 120. So no gauge, there's no round gauge that has ground speed on it. But that is a speed pilots need to be aware of. The good news is you're not going to calculate in flight if you have a GPS on board. All right, so ground speed is how fast you're going across the ground, and it does take into account the wind. So let's go back to indicator. Indicator, you notice this airspeed indicator I showed you yesterday, it doesn't have a knob on it to spin to try to make it more accurate. Indicated is indicated no matter what altitude you fly at. Calibrated takes into account that there are some errors. We looked at a Pitot tube out in the shop the other day, and it was pointed straight ahead. Well, what you pitch the airplane up really steep. You fly really, really slow, and you pull the nose up, and you fly really slow at a high angle of attack. The air's not going to go quite. That means I'm going to be flying the airplane compared to the way I was. The air's not going to go into that Pitot tube quite the same. So there's a little bit error. Sometimes it's called instrument error. Sometimes it's also called installation error. And if you take those errors are taken into account. The thing about calibrated airspeed, fortunately for us, is we don't have to worry about it too much because they put all the arcs and red lines and stuff like that on the airspeed indicator are all indicated airspeed. And the good news is if you're cruising at normal forward cruise speeds with the gear up, the flaps up, and a normal power setting, indicated and calibrated are usually really, really, really close, usually within a knot or two. A mile an hour or two. Okay. airspeed, on the other hand, you need a really good concept of this. So let's say you're flying along at sea level, and your airspeed indicator says 100 knots, and we'll say it's a standard temperature, 15 degrees Celsius, and it's a standard pressure of 29.92. And if your airspeed indicator says it's 100 knots, your true airspeed is 100 knots. Let's take that same airplane and let's go to 18,000 feet. If you recall from a couple of days ago, at 18,000 feet, half of the atmosphere is below you, half of it is above you. If I'm actually, and let's just say there's no wind. So when I'm near the ground, sea level, I'm doing 100 knots indicated on my indicator, and the ground speed says 100 knots. I go up to 18,000 feet and airplane, and I can do 100 knots indicated on the airspeed indicator. How much air is getting rammed into that pitot tube compared to how much air is getting rammed in there at sea level? Well, it would be half if I was going a different airspeed. But so I said for this, it was a trick question. So thanks for falling into it. I'll just cover the whole up, and you'll be inside. Just knock on the door and see if I dig you out. Just kidding. I think a better way to have explained it would have been like this. If you're flying at enough ram plus static to go into the pitot tube, 18,000 feet, and you go fast enough to have enough air, so the pressure and the static pressure also makes the airspeed indicator say, okay, got 100 knots indicated in both locations. At 18,000 feet, how many molecules are there per cubic foot of air? Half compared to sea level. So actually, in order to get to 100 knots indicated, I'm going to have to go faster than 100 knots ground speed. You can think of it like this. True airspeed is ground speed, is the same as ground speed, as long as there's no wind. But unfortunately for us as pilots, there's always going to be wind, so we pretty much never say it that way. The higher we go up in altitude, if you were flying the same indicated airspeed, the true airspeed would be faster and faster and faster. And I can't remember what number it is, but it's up in some 30-some-odd thousand feet. It's actually a rate of 1. So I could be doing 100 knots indicated, but I'm really doing 200 knots true airspeed. So let's say we're at that altitude of a jet, and my indicated airspeed says 260 knots. My true airspeed would be 520. 2 times 260. 520. Wow. What that is telling me is, and here's what's interesting, I only need the same amount of thrust up there at some 30-some-odd thousand feet or whatever it is. If I have a certain amount of thrust that'll push me along at 260 knots at that altitude, it's the same amount of thrust I need at sea level. So I'm burning the same amount of gas. But if I'm up at 30-some-odd thousand feet, I'm not doing 260, I'm doing 520. So where am I going to get the best fuel economy? We got 2 choices. I know you got a 50-50 chance. Jonathan. Yeah, we're going to get better fuel economy at a higher altitude. If there's less air in a given cubic foot, there's less drag. If there's less air, there's less drag. But let's just say if I have the flap and the gear up, I need 260 knots to keep this jet lifted up into the air. I'll still need 250 knots indicated at sea level. I'll still need 260 knots at altitude indicated, because you can write this down. Your lift is based on your indicated airspeed. Your lift is based on your indicated airspeed. So when you're maneuvering the airplane, you base it on your indicated airspeed. And you don't have to write this down, but when you're flying a big jet like that, there's probably going to be a computer in there that's calculating true airspeed for you, and you'll have it on a readout somewhere, but you're not going to look at the gauge and say, oh, here's my true airspeed, I got to do something differently. You're still going to look at the airspeed indicator. Now we're going to be calculating that. Let's say you want to fly from Reedley International Airport to San Francisco International. It's about 200 nautical miles. It's a little less than 200. We'll call it 200 nautical miles. And you're going to fly in an airplane that goes to 10,000 feet, and you want to fly at 10,000 feet. And I'm going to make up these numbers. But let's just say you can do 100 knots indicated at 10,000 feet. but that airplane's probably doing 120 knots true airspeed. And now your true airspeed. Then take into account the wind, figure out what your ground speed is and how long it's going to take you. Because you got to calculate how long it takes, because you got how much gasoline to put on board, because you got to be able to fly there and have at least 30 minutes of fuel reserve. And the AOPA Air Safety Foundation says you ought to have at least an hour for safety purposes. So as a pilot, we're going to, when we get into planning cross countries, we're going to get out a little flight computer. It's a mechanical gizmo, and we're going to enter it. And all you have to do is know what your pressure altitude is and your temperature, and you enter with your indicated airspeed, and it'll tell you what your cruise is. Did I lose anybody there? All right. So here. I know some of this we talked about yesterday, but I wanted to be really organized about it. So first I'm going to talk about the green arc. The green arc is the normal operating range. Does anybody remember from yesterday? The bottom end of the green arc, the slowest speed on the green arc. What is that speed? The slowest spot on the green arc. So that's right there. There's the low end, and then there's this end right down here. So this green arc, I guess I need to change the color here. So the green arc equals normal operation. What happens at this low end of the green arc down here? It starts to stall. Now, what configuration is the aircraft in? Tell me about the landing gear and the flaps at the low end of the green arc. Well, hang on a second. If you're flying really, really slow, you're probably doing one of two things. You're either just took off or you're about to land. So if you're about to land, I know you don't know a lot about flaps yet. You think it's a good idea to land with the gear extended or with the gear get up into the airplane? Shot here. Okay, if you said it's better if the gear is retracted, well, I guess there's a circumstance or two where that's a better idea, but most of the time you want the landing gear down under normal conditions. So flaps generate a lot of lift so you can fly slower, and generally speaking you put out the flaps or you extend the flaps close to, if not all the way, for most landings. Sometimes people call this dirty. The airplane is dirty because it's generating a lot of drag. The landing gear creates drag and slows you down. Although the flaps generate a lot of lift, they also slow you down. Remember, every time you generate lift, you also generate drag. So if you add flaps to generate lift, it's also going to add drag. So that's why pilots say, oh yeah, I was flying the airplane and it was dirty. That either means there's a lot of bugs and dirt on it, or the landing gear is extended and the flaps are extended. So the lower end of the green arc is the stall speed of the airplane with everything. In this case, it's with everything clean. Now, how about the lower end of the white arc? Let's talk about the white arc for a second. You might on white arc. White arc is the flap operating range. The white arc is the flap operating range. The low end of the white arc, you'll notice, is 5 or 6 knots slower. So in this case, you're gonna have your flaps out when you land? Yeah. So that's the stall speed of the airplane dirty, or stall speed of the airplane with everything extended. Or you could say stall speed with everything out. It makes sense. If you got more lift, you can fly a little bit slower. If you look at the upper end of the white arc, which in this case looks like about 91 knots, right there is the lower end of the white arc. That's as fast as you can go and have any of the flaps extended. If you fly faster than that, you need the flaps all the way up first. So if you're coming into land and the airspeed indicator is here at 100 knots, you have to slow the airplane down. Hold the nose up, pull the throttle back, and slow down. And the airspeed has to get down below, and I'll just make up a number, we'll call that 92 knots. It's got to be below 92 knots, and then you can extend the flaps. Then you can put the flaps out. Or you can say, then you can start putting the flaps down. So if we were going to call these things numbers, or here I'll show you, or letters. Ooh, darn, I thought I had done such a good job. White arc. We got to put the white arc in there. So the white arc is the flap operating range. And the green arc is the normal operating range. And the yellow arc is caution. And the red line is never exceed. And we did a little bit of this yesterday. So maybe I ought to do it like this. VSO is velocity of a stall. And the O, the way I remember it, O is with everything out. Technically, it's the velocity of stall in the landing configuration. But O equals out. So guess where that is? What did we just say? Where do you stall? This is the low end of the white arc. So this right here is the lowest white arc. So that's V, stall with everything out. While we're at it, we're looking at this stall speed here. It's velocity of stall number 1, and the way I remember it is that most of the time you're flying around with the landing gear up if the gear goes up, and you're flying around with the flaps up if the airplane has flaps, and most airplanes have flaps. So that's the primary configuration you're going to operate the airplane at, is clean. I wish they had called this VSC, but they didn't. It's called VS1. This white end of the white arc right here, which in this case is 92, is velocity of flap extension. That's VFE. So you ought to have VFE on your list there. It's the maximum speed you can have any of the flaps in any position other than all the way up. So it's the fastest speed you can fly with any of the flaps down. Let's see, so we got velocity, max, flap, extension. So there we got an F and an E. And we got VS is the velocity of stall, clean. Whoops. There we go. And VNO is velocity of normal, whoops, is max normal operation. And then VNE is velocity of never exceed. So on this airspeed indicator that we've been looking at, it has, well, I guess I'm not quite done here yet, going back to it. So let's see if I can remember it all. So down here, right here, this is velocity of the maximum velocity of maximum normal operation. That's the top of the green arc. This yellow arc here, that's the caution range. And the only time you can fly in that range is if you're in smooth air. That is, you cannot fly in the yellow arc if there's turbulence. It's more stressful for the airplane. Think about it like this. You're driving off-road in a Jeep, and the road's really bumpy. What's going to happen to how much you stress the metal of the vehicle if you drive on this really bumpy road? Is it easier on it if you drive faster, or is it easier on the metal if you drive slower? It's going to be easier on it if you drive slower. So at some point you could be driving that Jeep and you could hit a pothole and it could fall in it. You could actually bend some of the metal, right? Same thing with airplanes. The only time you get to fly inside of the yellow arc is if there's no turbulence. That is, it's a really, really smooth road. Or in this case, smooth air. Pardon me? Well, you not necessarily, no. You can have smooth air near sea level, middle altitudes, and at high altitudes. Doesn't make any difference. Now, are you more likely to get turbulence at low altitude? Probably, because there are some turbulence, like for instance, if the sun beats down on a hot chunk of asphalt like the Fresno Fair. Think about the parking lot, the Fresno Fair. It's a giant chunk of black asphalt. If you fly over it at 500 or 1,000 feet on a summer day at 3 in the afternoon, the asphalt has gotten hot. The asphalt sends out infrared radiation and heats up the air right above it. That hot air is less dense, like inside of a hot air balloon. That hot air is less dense, so since it's less dense, it rises. So you fly through it, and it's going to bump you up, and then in that column of air, you're going to fly past it. You might drop a little bit. So in that case, you might have some more turbulence at low altitudes. But there's some kind of turbulences that don't occur at low altitude, like the jet stream, but I'm not going to talk about the jet stream. So I probably would say, if somebody said, is it more likely to have turbulence at low altitude than high altitude? On a hot day, yes. On a cold day, no. Am I answering your question okay? All right. So here we have red line, and that's V and E. So the red line it means never exceed, and if your red line is on an airspeed indicator, it's the velocity that thou shalt never exceed. It's like one of the 10 Commandments. Well, it's not religious-based, it's physics-based. But if you go past this red line, the airplane and the elevator is stuck. That's my personal favorite flight control. If I had to lose the rudder, the elevator, or the ailerons, I would lose the ailerons or the rudder first, but not the elevator. Okay, I think I got it all. Any questions? So just as an example, here's a slightly different airspeed, and we could go really fast here. So here is velocity of stall with everything out, and here the bottom of the green arc is velocity of stall in the primary configuration, that is with the aircraft clean, with everything retracted. This green arc is normal operating range, and the white arc is the flap operating range. The top of the flap, although the highest flap operating speed is velocity of maximum flap extension. The top of the green arc right here is velocity of maximum of normal operation. We got the yellow arc, which is caution, and we can only fly in the yellow arc if there's no turbulence. And then we got the red line, which is never exceed speed, and that's velocity of never exceed. Did I lose anybody there? Okay, I guess I don't need to do that again. But here's just another, they forgot to put the little one right there. Dun, dun. Okay. So you recall from many days of lecture ago that airspeed indicator It was hooked up to the static source as well as the vertical speed indicator was, and as well as the altimeter. But unlike the vertical speed and the altimeter, which are only connected to the static port, the airspeed indicator is also connected to the pitot tube. And the pressure inside of the pitot tube is the ram air from going forward plus the static pressure that's already in there. So the pitot tube has ram plus static, and the static port only has static. So effectively, this airspeed indicator, when I say that it's a mechanical subtraction device, it's just the pitot, it's just pitot minus static, and the pitot tube is really ram plus static minus static. And then of course these two cancel each other out, so we're left with ram. And instead of that pressure being measured in pounds per square inch, it's measured in airspeed. Or if you've got an older airplane, it's measured in miles per hour. The airplane I fly was made in 1969. On the gauge, it actually says miles per hour, and on the inside, you can read the knots off of it. And I think they just did that to try to make people think it was easier to fly, because they used miles per hour, and that's what people in cars used, or still use. But I don't think anybody calibrates it in miles per hour anymore. So this technically right there, everything I did there except mechanical, I guess all of that, that's all a review. Does anybody have any question about that? I think we covered that on the first day. So I already covered the fact on another day that, here we go. Let's take a look and then we'll come back to there. So here's an airspeed indicator. There, you got to understand there's two holes on the back of the airspeed indicator. So one of them is static, and one of them gets pressure from the pitot tube. The static goes all the way inside the case. So that's just like the airspeed indicator and the vertical speed. All three of these instruments, the static system has a line going into it, and that's the pressure on the inside of this instrument. So the glass face, it's sealed on there. This case, this round black cylinder, is airtight. The pitot pressure comes here on the inside, and you'll notice there's this diaphragm, and it can expand and contract, and through these linkages, it makes the needle move. The question becomes, what if we were on the ground, and inside of here, well, we'll get to those here shortly. So I like the airspeed indicator. If I had to choose in flight which of these gauges I'd rather have, the vertical speed would be my least, the one I'd care about the least. And I'd be kind of torn between airspeed and altimeter, because the airspeed's telling me how fast I need to fly, but the altimeter's telling me how high above the ground I am. So I don't know, which do you want to do? Do you want to stall or do you want to hit the ground? Yeah, I don't think I want to do either one of those. So I'll go back here a second. What happens if you land at high speed? Well, your airspeed indicator will show a high speed. Remember, the wheels are not spinning. So as you come down and you touch the wheels onto the runway, they'll go from 0 to, instead, let's say you normally touch down at 60 miles an hour, and let's say now you touch down at 100 miles an hour, more of the rubber is going to come off of the tire and go on the runway. That's normal for rubber to leave the tire and go onto the runway. That's normal because the tires aren't spinning. There's been in the past, people invented things to get the wheels to spin, so when they touch down, they don't wear off. But the weight and the cost of that is worse than just buying tires more often. So nobody, I don't think anybody does that anymore. To the best of my knowledge, nobody's ever put that into production. So secondly, so number one, you'll wear out your tires faster. Number two, you're touching down at a faster speed, so you're going to need a longer runway. And you're going to have to use the brakes a lot more, so you're going to wear out the brakes faster. Now, it's not like the airplane can't handle it. You're not going to ruin anything. You're just going to wear the brakes out sooner. My concern is, if it was a short runway to start with, will I be able to stop before I get to the end of the runway, and will I go off the runway through the fence and into the ditch? and now I've ruined my airplane, and I'm very unhappy. And that's me why I was landing so fast. So that's one thing you're going to do when you go learn how to fly, is you're going to practice over and over and over again. You want to touch down in the first third of the runway, not touch down halfway down, not touch down most of the way down, but you're going to touch down usually within the first 500 feet of that runway, and you're going to fly from about 500 feet all the way down to the runway. You're going to fly at that slow approach speed. You're going to use as much flaps as you can. And if something goes wrong, you say, you know what, I'm too fast. I'm going to end up far too down the runway. You're going to do what's called a go-around, whereas you add throttle like you're going to take off, and you start climbing, and you get rid of the flaps slowly. We'll get to that later. And you're going to fly the traffic pattern and come in around and do it again. If you decide not to land, but you're lined up at the runway, it's called a go-around. And you're going to learn how to do that. And what the one problem with pilots, especially the ones that think they're all that, see how I didn't say the S word? They want to save the landing so they don't think they look stupid to other people, but it's impossible to save it. And so they end up landing halfway down the runway, and they're too fast, and they go off the end of the runway. All they really had to do was say, you know what, I made a mistake. I didn't get on it soon enough. Mistake. I'm just going to give it the gas. I'm going to go around and come do it again. So I think if you wanted to write down what are the top 10 things you need to be able to do to be a safe pilot, you need to look at what you're doing and decide if you need to stop doing it because you made a mistake and do something different and not worry about what anybody thinks. If you're on your check ride for your private pilot certificate and you're coming in to land at this runway and you're a little bit too fast and you're a little bit too high and you're not going to be able to make it, the fact that you say, I'm allowed to the examiner sitting next to you, I'm a little high and I'm a little my airspeed, I'm going to go around, and you give it the gas and you come back around and do it again, they'll actually think you're a better pilot because you're willing to evaluate yourself. What are you doing? Am I doing it well enough? And if I'm not, how do I get out of this situation and do it safely? Not how do I get out of this situation by getting the airplane on the ground and doing it unsafely. So you need to think about that. If the way your brain works is that you're not willing to admit that you can make a mistake, you're not going to be a safe pilot, because I'm telling you, you're going to make mistakes. You're going to make mistakes. You're going to make mistakes. But effectively, as a good pilot, it's every few seconds, every 5 seconds, every 10 seconds, you evaluate what's happening and you decide. You don't have to worry so much about how you got there, although sometimes that is important. The question is, what do I do from here forward to be safe? And see, I've been flying a long, long time. I'm glad you asked this, because I've been thinking about this for the last week, because I read an online article about experienced pilots, and they don't practice doing a go-around. And so when it's time for them to do a go-around, they don't know how to do it very well. And I realized that the airplane I fly, I can land it in about 700 or 800 feet. And the runway out at Reedley is like 2,500, 3,000 feet. So it's 3 times longer than I need. So I can actually land halfway down the runway, and I'm still okay. So what's happened is that I haven't done a go-around. I don't remember the last time I did a go-around. I don't think I've done a go-around for 2 or 3 years. And it hit me, wow, I think I need to practice that because I haven't done it. And I didn't say that to myself because, oh yeah, because I'm such a great pilot, I haven't had to go around. No, it's been in this airplane for 10 years, and I'm in airports that the runway is really, really long, and I can get away with it and still be safe. So then I decided then, it was last week, is that next time I go flying, I'm going to deliberately come and try to do it correctly. And even if I'm doing it correctly, I'm going to say, okay, I'm going to practice going around. Because when you give it the gas to go around, the propeller generates more thrust. It goes across the tail, and the tail you've already got, it's used to not having much air on it, so you're holding the nose up. As soon as you give it the gas, the nose tries to go way up, and if you don't do anything about it, if you don't push on the wheel, the airplane will stall, and at 200 feet above the ground, you won't be able to recover. You'll hit the ground, and you'll probably die. So practicing a go-around, when you give it the gas, you got to push forward on the control wheel and then give it some trim. And I realized I haven't done that for a couple of years. Oh wait, I was going to talk about that slide there. So the static pressure goes to the inside of the case, and the pitot pressure goes to the inside of the diagram. It goes to the inside of the diagram, the diaphragm. And then as the diaphragm expands and collapses, the airspeed indicator needle wiggles. So of these three instruments, this is the only one that needs static and pitot pressure. The other two instruments are only supplied with static pressure. This one is supplied with static pressure and with pitot pressure. And of course, the pitot pressure is made out of RAM plus static. Okay, why are those slides blank? Okay. So we talked about calibrated airspeed versus indicated airspeed. So I mentioned that calibrated airspeed takes into account that the pitot tube isn't aiming straight into the wind. So that's why indicated versus calibrated is not exactly the same. You could also enter a skid or a slip. And let's see, draw a little picture of that. So let's say here's your airplane and you got a propeller on front, and let's say here's your wing, and the pitot tube is out here outside of the propeller. So wind is hitting it relatively straight. But what if I jammed in a bunch of rudder and I made the nose of the airplane go this direction? Or you could say here's the wind, and now the airplane is flying through the air because I've stuffed on the rudder, and the pitot tube is right here. You notice the wind isn't going straight into this tube anymore. It's coming in at an angle. So it's not going to go into that pitot tube the same way it would. Also, let's see, here's my propeller. What if I've got the static port on the side of the airplane? Maybe the air will get stuffed into that static port a little more than it normally would. There are some airplanes that this is such a big issue, they put a static port on both sides of the fuselage, so if one gets a little bit too much air shoved into it, this one doesn't get enough air shoved into it. It tends to equalize it. So a slip or a skid is when the airplane's going in one direction, but the nose is pointed off at a slight angle, and it's typically because I either have too much rudder or too little rudder in there. And that could cause the airspeed indicator to be incorrect. Ta-da! Oops. Everybody get that? Who's not happy yet? All right, so let's just say your pitot system, your pitot tube gets blocked. You know what? I just realized that I forgot to tell you something. So if we go back to the airspeed indicator, and here's the pitot pressure going in this hole, and here's the static pressure going in here. What's going to happen to this static pressure, the static pressure, if we climb in altitude? What's going to happen to the static pressure going into this instrument? We're going to a higher altitude. What happens to air? If we go to a higher altitude, the air, it does what? It creases? Creases which way? Does it get hotter or colder? It gets colder. Does it get less dense or more dense? It gets less dense. If we wanted to talk about it in pressure, as you climb up, what happens to the pressure? What's that? It increases? Try again. We go to a higher altitude. Is there more pressure up there, or is there less pressure? There's less pressure up there. So if this side of the airspeed indicator is hooked up to the static port on the side of the airplane, and we climb up in altitude, is there more or less static pressure inside the altimeter? Less. Okay. And that's good because remember that calculation. We've got static. We've got to have static in the pitot tube, and we've got to subtract static coming out of the static port. So all the time we're left with RAM. Okay, so the static pressure going into the pitot tube, if we go to a higher altitude, it gets less. So we need the static pressure going into the to the airspeed indicator also to get less. If we clogged this hole, let's say we're at sea level, and the static port on the side of the airplane got clogged, and no static air could come in and no static air could go out, then the pressure inside of here would be at 29.92, and it would never change. But this pitot pressure, remember the pitot pressure, it's RAM plus static. But if we say this fly the same speed, but we climb in altitude, static pressure gets less. So this is going to equal less total pressure as we climb in altitude. So our airspeed indicator, even if it was at 100, it'll show less even if we're flying the same airspeed. In order to do that math problem correctly, this mechanical device, we've got to have the outside static pressure to be adjusted. Just like this static pressure down here is changing, we need this static pressure coming inside the case to change. Otherwise, the airspeed indicator will not read correctly. I think that's going to do it for today. We'll do the blockages